Hello and welcome to today's podcast, Calorimetry and Specific Heat, beginning with specific heat. So we're going to be doing the targets up here at the top. Understand and apply the definitions of heat capacity and specific heat, some new vocabulary possibly, and then to calculate the amount of energy transferred between objects. Calorimetry essentially is the way that all of these enthalpies that we're going to end up with were originally determined. It's an experimental method that measures heat flow or heat exchange. Since we can't measure the actual system, both delta E and delta H, you had a situation where you can't measure the internal energy or the enthalpy, you can only measure the change in it. That's what this part is talking about. And then for the third bullet here, we can use the relationship between the system, surroundings, and universe to form a very powerful idea that's used throughout thermodynamics. And that is what the system loses, the surroundings gain, or vice versa. So that essentially the value, the magnitude of energy exchanged is the same. You just perceive them as having different signs. All right, the vocabulary that you're working with are two new words, and they're heat capacity and then specific heat capacity. Heat capacity itself is an extensive or extrinsic property. It doesn't matter how much sample you have, and so you end up with essentially the amount of energy required to heat something up. So heat capacity, how much heat can it hold? But specific heat capacity is more specific. Rather than being just how much energy does it take to heat anything up, it's how much energy does it take to heat 1 gram of an object up or a substance up. The other day we looked at the energy conversion between joules and calories, and we saw 1 calorie, little one, was 4.184 joules. That relationship came from the values for the specific heat. Water is also noticed 4.18 joules per gram degrees Celsius. So that's the amount of energy required to raise 1 gram of substance by 1 degree Celsius. So those units become very important, as does memorizing the one for water. All right, the specific heat is essentially, if you just look at the units for it, joules, quantity of heat transferred, grams, amount of material, and then degree C, amount of temperature change. And that's equal to the specific heat. The equation we generally use simply rearranges it, and we say Q equals MC delta T. So what this represents is, this is our heat. In many cases that ends up being our enthalpy. M is mass in grams. C, or it could also be S, is the specific heat. And that value is dependent entirely on what the substance is. Every substance has its own specific heat. And then finally, change in temperature. T final minus T initial. So we're not going to play around with your basic MCAT equations here. We're going to go right into a calorimetry problem where we're going to take two things into consideration. We're going to have both the MCAT equation, and then we're also going to have the idea of the heat lost equals heat gained. And so heat lost would be negative, and then the opposite one would be positive. Or you could denote them vice versa. It just depends how you want to set it up. All right, so for exercise 8, which hopefully you have, if not, you can go look on my PISD, we have a cup of coffee lost 24.1 kilojoules. All right, so I'm going to write down a bunch of given information. We're going to mess with it. Since this is giving me an amount of energy lost, that tells me that Q of my coffee is negative 24.1 kilojoules. When cooled from 60 to 37 degrees Celsius. So from that I can get my delta T. It's T final minus T initial. So when I subtract those two things, I can get an individual value here in just a second. If the same amount of heat is used to warm a piece of aluminum, alright, so now I actually have an unknown. It's going to be Q of aluminum. It's going to have to be the first thing I find out. Weighing 250 grams, so I have mass of aluminum. Decimal point. What would the final temperature of the aluminum be? Oh, we have another one. T final aluminum. If the initial temperature is 37 degrees Celsius. So T initial aluminum is 37 degrees C. And then it also tells me the specific heat of the aluminum, 0.902 joules per gram degree Celsius. Alright, I have a lot of information here, a whole lot of it. One thing that I need to recognize here right off the bat is that I am trying to make these two Q values equal in magnitude but opposite in size. Okay, so what I have here is, I'm not going to write a particular equation. Well, I guess I will write an equation. Because what I really care about here is I care about the aluminum. Because I know the Q for the coffee is equal to the Q for the aluminum, except opposite in sign, that's going to tell me something important. And then I'm also going to be able to use Q equals MC delta T. So 106.87 minus negative 37 tells me that the T final is 144 degrees C, including significant figures. Okay, quick recap. In the givens, I had a tremendous amount of information, but the information that I cared about was the fact that the Q of the coffee had to be equal but opposite sign to the Q of the aluminum. I did not use the original delta T for the coffee. I did use the mass of the aluminum and the initial temperature of the aluminum and the specific heat of the aluminum. Then I used the relationship equal but opposite and MCAT, plugged in my values, made sure my energy units matched up here, solved it for delta T, which is T final minus T initial, plugged in the T initial that I was given in the problem, and then solved for that. Watch it again if you need to, or come ask questions at will. In the next exercise, exercise 9, we're still dealing with coffee and aluminum. We're just doing it in a slightly different format. So this time you want to cool down a cup of coffee, and you do so by dropping in a cold block of aluminum. The aluminum block has a mass of 250 grams, so again I'm just going to go ahead and start by writing out all the given information that I have. Mass of aluminum is 250 grams. You want to cool 250 grams of coffee. Okay, and then it also tells me the specific heat of the coffee, which is mostly water, so that makes sense. 4.2 joules per gram degree Celsius. From 60 degrees, so T initial coffee equals 60 degrees C, to 45 degrees C. Alright, to accomplish this, what must be the initial temperature of the aluminum block? So we're looking for Ti aluminum here. From the previous question, the other thing that we need to grab out of that is the specific heat for the aluminum. We were told was 0.902 joules per gram degree Celsius. Okay, the other factor here that we really have to take a look at again is that the Q of the coffee is equal but opposite in sign to the Q for the aluminum. Heat from one is going into the other. Alrighty. The easiest way to set this up is actually to set up two equations right next to each other, because Q equals MC delta T for the coffee has to be equal to Q equals MC delta T for the aluminum. So the equation that I set up is just going to be that. Mass of the coffee times C of the coffee times delta T of the coffee equals mass of the aluminum times C of the aluminum times delta T of the aluminum. That'll at least give us a place to start. So as I start substituting in here, we'll start recognizing some things that might be useful. First, we have our masses. The mass of our coffee was 250 grams. Specific heat, 4.20 joules per gram degree Celsius. And then delta T is T final was 45. T initial was 60 degrees C. I should have written smaller. On the other side, the mass of the aluminum is 250 grams. Specific heat, 0.902 gram degree Celsius. And then I don't know about what's going on here, at least not yet. So we have, that's our overall equation. MC delta T for the coffee has to be equal to, but opposite in sign, of MC delta T for the aluminum. So I suppose I should take this whole equation and make that value negative. Alright, so let's solve some things out, or maybe simplify some things. You can either, if you note both of these masses are the same, so you could cancel them out. Your other option is to solve this whole side, solve this side, and then we can go from there. When I solve all of this, 250 times 4.2 times negative 15, I get negative 15750. Grams cancels, degrees C cancels. That leaves me with joules on that side. On the opposite side, 250 times 0.902 gives me 225.5 times delta T. This side, however, is negative. Now I have a negative and negative, so that becomes a positive issue. Makes things a little bit easier for me. So 15750 divided by 225 gives me 70. Oops, sorry. 15750 divided by 225.5. That makes things a little different. 69.845 equals delta T, which is T final minus T initial. That looks like we have two variables, but we really don't. And what I would invite you to think about is, if you took this block of aluminum and you stuck it into the coffee, when is energy going to stop being transferred? And the shorter answer to that is energy stops being transferred when both objects are at the same temperature. So that means that our final temperature for our aluminum is the same, has to be the same as the final temperature for the coffee. And that was 45 degrees C. So we have 69.845 degrees equals T final was 45 degrees minus T T initial. As we solve, that means we end up with 40, essentially we have to move all the minus signs and plus signs around to get this by itself in the positive form. So as we solve for Ti initial, we end up with 24.84 degrees C negative is the initial temperature for the aluminum. So that was one cold block. If you have questions or you're not sure about how to do the math on that last part, please come ask.